my name is Kevin Blacktop. I'm the chair of the National Robotics Network, and welcome to our presentation sharing the cost and risk of applying robotics. Firstly, I'd like to apologise. We've had a few technical hitches, which has delayed this presentation, so I do apologise. We will be beginning this presentation with some videos of industry challenges and developments being undertaken by some of our members. And we will follow this by a brief introduction into the National Robotics Network and the roadmap that we have been developing. And following this presentation, we'll be hosting a follow-on session, which will give us the opportunity to engage with you better. I'd now like to start with the videos. So I'd like to introduce Darren Potter of the National Nuclear Laboratory and the videos that he's provided, which show some of their recent developments. Thank you.
These demonstrations are about new tools and equipment that's out on the market. It's a joint effort. We're working with the oil industry, we're working with local companies.
We are facilitating 4 events. These demonstrations will be held over a period of time. The first one being the WASDALE event, which was delivered for the SL dive team.
So the technology that we're bringing from the oil and gas industry and demonstrating today is around cutting underwater.
We've deployed 3 ROVs as part of this collaborative approach today to demonstrate the capabilities. So the Outland 1000 was the first one to be deployed, and then alongside that we had the Video Array Pro 4 in there.
So today's been a good collaboration between the innovation teams and the end users.
So all in all, it's been a really successful day. Demonstrations again at the dive team in WASDALE, and with the demonstrations we're doing today is to allow people to see the capability of what these ROVs can do for us.
And I think having that ability to draw on, other sectors in order to demonstrate what we're able to do, and also allow us to get all aspects of both end users, operators, technical demonstration.
We've brought experts in and we've made a difference.
DELAFIELD is one of the 4 legacy ponds and silo sites. The site comprises of 24 concrete silos that have been built in the early 1960s and extended 3 times since, and are still undergoing decommissioning. Each silo is the size of a double-decker bus, housing the waste within a body of water.
The site has never been designed to be emptied, so no plan was in place for removing of the waste from these silos, making it challenging as the waste retrieval solution has to be designed around the current silo that can operate in a safe and reliable way. Current removal operation consists of a large machine enclosing itself around the silo, which has a grabber that is lowered into the silo to pick up the material and drop it into an enclosed waste bin to be transported and treated. Then safely housed, which will ultimately reduce risk to the public and overall costs. As we are looking ahead of time, we can see that the current removal operations are mostly clearing out the center portion of the waste, leaving a buildup of waste near the sides of the silos. This can cause potential issues in the future, one of which is not being able to clear the material around the edges, and another where the swarf collapses on itself, potentially trapping the grabber during its operation. To combat this, we are investigating potential solutions for the future, one of which is making use of an underwater remote operated vehicle, or ROV for short, to move the swarf from the unreachable sides, leveling out the waste and mopping it into the space reachable by the grabber. National Nuclear Laboratory, NNL for short, carried out the investigation on the potential of introducing the ROV as the solution, where the trials were conducted at the NNL's Workington site with the help from Underwater Vision ROV specialists, who supplied and modified the ROV for moving the swarf and have sent trained professionals to operate the ROV during these trials. To create similar conditions for what the ROV is supposed to tackle, these trials are an approximate of what is to be expected to appear within the silos, where a simulated Magnox alloy swarf, which is just like the real stuff but hasn't been in contact with the nuclear material, so it's safe to be around, is positioned within the corner of a pit to simulate a buildup of the swarf. In real-life applications, no one can enter the silo due to the hazardous material. To mimic these conditions, separating screens have been set up as a wall between the operators and the ROV, and the operators will rely on the ROV's onboard cameras to have a direct view of the scene, just like in real-life conditions. The pit we're using to demonstrate the ROV is filled with clean water, but due to the sludge residue on the swarf, which is a further degradation stage of the swarf, makes the water become slightly clouded, which is what the water is within the silo too. This worsens visibility and becomes one of the challenges the ROV operators have to deal with. During the trials, we've also had several cameras set up around the pool to capture the performance of the ROV as it shifts the swarf. We included another ROV equipped with an onboard camera to provide a third-person view to see if it will assist in operations, and to provide a safe and flexible method for recording footage underwater. The goal of these trials is to assess how easy it is to operate the ROV, to move the swarf, to find out if it's powerful enough to move and dislodge the swarf from the waste pile, and to evaluate the rate of volume shifted. During these preliminary trials, the visibility with the water became quite challenging. However, operators managed to continue with the task, shifting a significant amount of volume at a rate of 0.63 meters cubed per hour, and reduced the height of the heap from 2.1 meters to 0.9 meters across the 5 hours of trials. Overall, these trials have been very successful. It's given DELAFIELD and NNL the chance to once again reach out to collaborate with external companies to bring innovative solutions and the opportunity to gain more insight about the technology, its capability, and suitability on site in the future. The work towards implementing this technology will be reviewed and further investigated to ensure the potential deployment of this technology in the nuclear sector is done with confidence, reliability, and consideration for the future.
Now, James Kell will introduce some of the work being undertaken at Rolls-Royce to develop ways to inspect and maintain jet engines in situ.
Hello everybody, my name's James. I work for Rolls-Royce. I'm a technology specialist in the field of in situ inspection and maintenance. So what that means is we're interested in development of tools or techniques that we can take to an engine that's installed on an aircraft and perform some sort of surgery on it. This enables us to ensure that the engine stays on wing or as part of the aircraft for as long as it's supposed to, and enables us to generate revenue that way, rather than taking it out of service, causing disruption to not only our customer, but to ourselves as well, when we have to put it through our own overhaul shops. So to do that, there's a lot of restrictions that we have around us. So if you sort of see on the second slide, the kind of thing, when you walk up to an engine, all of the cowlings are down, and once you lift them up, you see on the third slide, we're basically an exposed big tube, really. And what that tube has is a range of inspection ports that go from about 4mm to 13mm. And that's really all we have as a way of getting inside to perform some sort of corrective surgery. And we're pretty good at that. Our teams are very good at kind of going out and performing lots of routine visual inspections or non-destructive testing inspections like ultrasound, eddy current, etc., to look for anomalies. But also we're quite good at performing repairs too, with and all with off-the-shelf pieces of a kit, and all with lots of skill from our skilled kind of mechanics. But there are other things we're interested in doing as well, like the more tricky tasks, for example. And that's the kind of thing where we've been looking at developing our own supply chain, because there's lots of this stuff that doesn't exist already. So we've had to kind of go back to the drawing board in lots of ways and work with universities and other technology suppliers to put together a big, long technology supply chain that results ultimately in a device that we could go and use. And you'll see that there's a huge amount of customization that's been kind of placed on those things. So as by way of kind of example, I'll show you the first video, which is to do with a robotic bore blending device that we devised. So working with the University of Nottingham and funded by Aerospace Technology Institute, you'll see in this video a kind of a collection of clips really that describe some of the issues that we face on a day-to-day basis. So we've got an example of a colleague there doing some effectively like dentistry work almost on a compressor blade to remove a piece of damage. But what we did with the University of Nottingham in this case is devise a robotic way of doing such a thing. So we thought, rather than sending the person to the job, we could have a collection of robots placed out in the field that could be remotely controlled by a person that's perhaps more centrally located. This means that our specialists can be better utilised, and we have potentially a better or quicker speed of response. So this is all done in the lab at the moment. We're just demonstrating that in a lab environment. Actually, it's a few years old now. We're kind of in a place where we've used a lot of this technology in different ways, not quite as you've seen on the screen here, but actually what's going on is we're actually kind of creating a virtual representation of that blade, and then kind of sending that machining data over the cloud effectively to a robot, which then performs the surgery and enables us to put the engine back together and let it go on its merry way, if you like. So that's one example really of how we've looked to develop our own special tool to provide us with a way of performing corrective surgery. So just also like to show you another animation, actually, this time of another project that's in a similar vein, both in terms of it being intended for in situ or on wing use, and this time we're looking at putting a coating back on rather than removing material that you saw in the previous video. So in this case, we're looking at potentially putting two snake-like robots into the combustion chamber, so they can actually kind of work in a collaborative or combined way to firstly inspect the area of coating in question, and then also to clean it up and then put some coating back on. And this has been done again in partnership with Aerospace Technology Institute, part of an Innovate UK funding, with our partners Metallisation and the University of Nottingham in this case. So Metallisation have been working on a flame spray application method, and the University of Nottingham have been using their expertise in making snake-like robots for our needs and uses. But really just hints at the fact that there's nothing really out there off the shelf that we can kind of put our hands on and use, other than things like flexible video scopes, for example, which are great, but they're limited, and we can do some really good remote visual inspection with them. But when we have to look at more tricky tasks, as I've said, about kind of putting coatings back on and performing repairs where we kind of require some skill to actually remove some damage. That's when we're basically into customized robotics. And we really wouldn't be that keen to be doing customized robotics because it kind of, it takes a long time to develop that. It's relatively costly in terms of putting in our own funding to do so. But it just feels like there ought to be a better way. There's plenty of stuff I'm sure that we've developed with our own customized things, and I'm sure you've seen with other sectors that Kevin will have introduced from a National Robotics Network perspective, whereby actually we could use potentially some other of those building blocks to get to our solution quicker. And likewise, we feel like potentially we've also broken ground in some areas where we might have some transferability to other areas of interest. So kind of outside of our own sector, potentially even into the medical world, for instance. It'd be great if things went full circle, because some of the things we've been doing have their basis and genesis, if you like, in the medical industry. And really, if we're able to kind of take things back into the surgery world, that would be a wonderful kind of closing of the circle, so to speak. But that just really is some kind of an example of why we are engaged with the NRN, because we share their vision of having a kind of or developing the cyber physical fabric, if you like, for the UK to prosper, particularly in this kind of this new Brexit world, where we are able to have a kind of more coherent UK PLC strategy for the robotics sector as a whole. So I'm keen to see what else we're able to discuss and move forward on this topic. Hopefully speak to some of you soon.
I'd just like to provide a quick update because we had the technical issue at the beginning. We've actually modified the time to our follow-on session to 12:30. So we've just moved that back 15 minutes so that we can continue to have the same amount of time that we planned to have with you if you're joining us for that event. Now I'd like to introduce some videos by Professor Samir Nefti-Miziani from the University of Salford. And this is the work on manipulators and handling systems that suit a variety of applications.
Good afternoon. My name is Samir Nefti-Miziani. I'm Professor of Artificial Intelligence and Robotics. I'm Executive Member of the National Robotics Network. My talk will be about handling system for cross-sector application. One of the main common problems that different industry sector faces is handling of products. For example, in material handling and logistics sector, there is a requirement of one handling system that could be used for packaging construction, material movement from place to place, storage, retrieval of parts, or inventory, without having to change end effector all the time. Similarly, in space sector, for example, the spent rocket stages consist about 18% of space debris. Then removing orbital debris known as a non-cooperative target using robotics arm will require ideally a simple dexterous AKM nozzle handling system that is versatile and able to capture various non-cooperative space targets without a prior knowledge about the object, and ideally also without the need of using a vision system, which could be a problem in this type of environment. Another interesting sector where handling system is required is food sector. Within the UK, food manufacturing is by far the largest manufacturing sector, having a turnover of approximately 80 billion euro per year. Despite its enormous dense size, the food industry has been slow to see the benefit of automation. One of the most significant challenges faced by the robotics and automation industry is the grasping food product. Food product can vary enormously. They might be sticky, slippery, wet, flexible, delicate, or deformed when handled. This means that traditional end effectors such as vacuum or jaws cannot be used. Sort out strawberry for packaging, which you can see here in this photograph, require quality control. This task is always performed manually as end effectors do not exist capable of grasping them without causing damage. Therefore, there is a need of building a multifunctional gripper that could be used in ideally 3 sectors. Then when you look at the off-the-shelf robotic gripper are most suitable are not suitable for cross-sector application. Typically, they have limited dexterity, they are suited to one or small number of products only, and have little or no feedback touch at all. They are suitable, as I said, when all the products are identical, but what about when the product size has large tolerance? What about when, if delicate deformable products, what about if it held the lifted object slips? Then to address the technical challenges, then for a cross-sector technology, we have developed a multifunctional and multi-purpose gripper, which is low cost for SME. We have added more capability to the gripper to allow the manipulation and regrasping actions that change the pose of the held object in the hand, and which allow it to be more dexterous. For this gripper, then gravity, inertial motion, and external contact from the environment can be cleverly exploited to change the pose, as you could see, of the grasped object relative to the hand. Another application of the cross-sector gripper was in space. Then, as you can see, using the space underpinning technology used for grasping food product, it has been used to resolve the handling challenge in space. It uses synergy principle. It allowed to grasp blindly many types of objects and payload without prior knowledge. This photograph shows a heavy load test bed, which uses the 2- and 3-fingered grippers. One arm will act as the manipulator of the service space vehicle, while the second will perform the relative movement of the target vehicle to the service vehicle. But this test bed is also used to show the collaboration between the two grippers in space. The space sector has already developed a grasping method using an off-the-shelf gripper. However, it's not a multifunctional gripper. It requires an RGP depth sensing for orbital condition, and also it requires a state and parameter identification such as pose, angular velocity, the inertial parameters, the grasping point and contact points. Again, the same gripper has been used for packaging, construction, material movement from place to place, as you could see. And finally, we have extended the use of that technology to another sector, which is the nuclear. As you could see, the same handling system is being used to grasp all the objects in nuclear use case. Then it was used for the competition funded by NDA, DELAFIELD, Innovate UK Base, led by Jacobs. Then this is a 45-kilogram version of that gripper, and we can see the performance of it in this sector as well. Thank you.
The NRN was formed by the industry partners of the EPSRC Autonomous Intelligent Systems Partnership Programme. The industry partners came from a variety of sectors, but very quickly realised that they had similar challenges. With the help of KTN, we have continued to work together as an open network of end users, supply chain and academics. And as you can see from the list, we operate in a wide range of sectors. We believe that cross-sector collaboration will benefit both the end users with affordable solutions and technology providers with a greater market opportunity. The NRN is end-user driven because we need industry pull to identify useful technology and applications. Industry pull will enable new developments to bridge the valley of death because the final stages of implementation require end-user support. Many sectors have specific supply chains. RAI technology is often very bespoke and therefore expensive and has not been widely adopted, particularly in smaller businesses. Greater market understanding beyond a specific sector provides the opportunity for bigger volumes and therefore cost competitiveness. The whole ecosystem from academia to end users all have their part to play, whether it is communicating needs or developing solutions. these activities cannot be done in isolation. One of the biggest challenges for RAI technology is to be adopted by smaller businesses in the UK. They need affordable RAI technology that can be adapted to suit their business needs. This may drive us towards more modular systems rather than bespoke. The NRN members agreed to fund a roadmap to establish common end user needs and to identify the current technology baseline. We want to drive the technology solutions to ensure they add value and help develop the supply chain. Encouraging other sectors to get involved will further enhance the roadmap. We have identified 5 key themes and 10 areas of collaboration that we believe will have a significant opportunity for development across multiple sectors. These are sensing and perception, mobility, manipulation, AI and autonomy, and the human-robot interaction. The key themes and areas of collaboration have been mapped out against a number of sectors, which will allow us to ultimately prioritise the development opportunities. There are, of course, many barriers to common supply, but the benefits outweigh them. Affordable and flexible RAI solutions come with volume, and industry and task bespoke solutions will remain unaffordable for many end users. Thank you very much for joining us for this presentation. We very much hope you enjoyed it, and we'd like to invite you to join our follow-on session, which is just starting right now. It's an opportunity for us to engage with you better, get some questions and answers going. So please join us there. Thank you.